So in this lesson, what we're going to do is we're first going to look at neutralization reactions, looking at weak bases with strong acids, weak acids with strong bases, and strong acids with strong bases. And then what we're going to do is we're going to analyze the salts that are formed from these neutralization reactions. So to get started with, to write a neutralization reaction, you're going to have an acid and a base. So let's first look at strong acids and strong bases. So here I have hydrochloric acid and sodium hydroxide. So hydrochloric acid reacts with sodium hydroxide. Keep in mind this is a double replacement reaction, so what it's going to produce is water, H2O, and NaCl. So you've got NaCl and H2O. Now, that's as far as we have really gotten, except for the fact that you now need to consider your solubility rules. Keep in mind when you have a strong acid and or a strong base, they are strong electrolytes, meaning they're going to dissociate completely into their ions. And so in order to write the net ionic equation for this, I need to break apart any strong electrolyte. So hydrochloric acid is a strong acid, so that's going to be hydrogen ions plus chloride ions. And sodium hydroxide is also a strong base, so it's going to be sodium ions and hydroxide ions, and that's going to produce, well, sodium chloride is soluble, so it's going to be sodium ions and chloride ions, and then that's going to produce water. So keep in mind to write your net ionic equation, you will eliminate anything that stays the same on both sides, anything that is a spectator ion, so the sodium ions and the chloride ions will be eliminated. So your final reaction, your net ionic reaction for this, is going to be hydrogen ions reacting with hydroxide ions to form water. And so that's all it is with a strong acid and a strong base, because you're able to eliminate two spectator ions. Let's look at a strong acid and a weak base. I've got hydrochloric acid and zinc hydroxide. So I've got hydrochloric acid here, reacts with zinc hydroxide, and it's going to produce, well, zinc chloride and water. Now it's my job to determine what's soluble, and therefore I should break up into its ions. So hydrochloric acid is a strong acid, so I'm going to break it up into its ions. But first, I need to balance. I'm going to put a 2 in front of hydrochloric acid and then a 2 in front of water. Now I'm balanced. Now I can write the full ionic equation. So I've got 2 hydrogen ions plus 2 chloride ions reacts with, well, zinc hydroxide is a weak base, and so therefore it's a weak electrolyte, therefore it's not going to break up into its ions. And that produces, well, zinc chloride is soluble, so it's going to be zinc ions plus chloride ions and water. Okay? So the only ions that I can eliminate that are spectator ions, well, it's just the chloride that I can eliminate, because everything else changes over the course of the reaction. So I've got 2 hydrogen ions reacting with zinc hydroxide, which produces zinc ions and water. Okay? Let's look now at a strong base and a weak acid. So here I've got sodium hydroxide and hydrofluoric acid. So sodium hydroxide reacts with hydrofluoric acid to produce, well, it's going to be sodium fluoride and water. Okay. I'm already balanced here, and so I'm just going to break apart any strong electrolyte. So sodium hydroxide is a strong electrolyte because it's a strong base, so it's going to break apart into sodium ions and hydroxide ions. Now the hydrofluoric acid is a weak acid, so it's a weak electrolyte, so it's going to stay together, and that's going to produce sodium fluoride. Well, that's going to break apart. It's going to be sodium ions and fluoride ions and water. And so the only thing that stays the same, that is a spectator ion, are your sodium ions. And so as a result, you're going to have hydroxide reacting with hydrofluoric acid to produce water and fluoride ions. All right? So keeping in mind that if you have a weak acid or a weak base, since they don't completely dissociate, you're not going to just end up with a net ionic reaction of hydroxide reacting with hydrogen ions to produce water. Now the issue comes along when we're looking at salts. So whenever we have a neutralization reaction, water and a salt are going to be produced. Now the question, what we've assumed so far, is that that salt is neutral, and that's not actually always the case. So what I'm going to do is I'm going to provide you with an example, show where the salt comes from, and then explain whether the salt is acidic or basic and why. So what we need to do is decide whether each of the solutions that's formed from the following salts is going to be acidic, basic, or neutral. So let's look at an example. Here I've got potassium fluoride. Now, we've got to figure out where this potassium fluoride came from. Well, if you think about it, the potassium had to come from potassium hydroxide because that's where your metal comes from. And then the fluorine had to come from hydrofluoric acid, because that's where your anion comes from. So the reaction that occurred was potassium hydroxide reacting with hydrofluoric acid, and that produced water and your salt, which was potassium fluoride. Okay, so what's key here is for us to look at potassium hydroxide and look at hydrofluoric acid. Remember, if you have a strong acid or a strong base, then the conjugate acid or the conjugate base is going to have negligible basicity. So for example, potassium hydroxide. Potassium hydroxide is a strong base, which means its conjugate acid, which would be the potassium ion, the K+, it is not going to be acidic at all because it came from a strong base. Hydrofluoric acid, however, is a weak acid, which means its conjugate base will be basic. And therefore, the fluoride ion, that F-, is going to be basic. And so as a result, one question that could be asked, first of all, the answer is that solution is going to be basic. Let's make sure we understand why. So the fluoride ion, what I could ask you to do would be to write the hydrolysis reaction for this fluoride ion. So I would take fluoride and I would see how it reacts with water. I know it's going to be a base, so what it's going to produce, since bases accept, it's going to become HF, and water will become hydroxide. And so the first step in these problems is identify whether your solution is basic, acidic, or neutral, looking at or thinking about where your anion and your cation came from. Potassium ion came from hydroxide, from potassium hydroxide, therefore we don't even consider it to be an acid, while the fluoride ion came from hydrofluoric acid, and therefore it's going to be basic. From there, now that I know that the fluoride ion can act like a base, I can write out a reaction just like what I had done before with other weak bases. Let's look at one more example. Here, I'm given iron chloride. Now, iron 3 chloride, if you think about it, the iron came from iron hydroxide, okay? And the chlorine, the chloride ion, came from hydrochloric acid. Now, iron 3 hydroxide is a weak base, which means that iron ions can act like acids because they're the conjugate acid. Now, the chloride ion came from hydrochloric acid, which is a strong acid, therefore I'm going to ignore chloride. So iron is responsible for the fact that this solution is going to be acidic, and so we could even write out a reaction with iron acting like an acid. But for this problem, I just want you to determine whether the salt is basic, acidic, or neutral. Now, one example of a neutral salt would be NaCl, sodium chloride. The reason why that's neutral, well, the sodium came from sodium hydroxide, which is a strong base, and the chloride came from hydrochloric acid, which is a strong acid. Therefore, both the cation and the anion came from strong acids and bases, and therefore it's going to be a neutral salt. So let's look at an example. Here it tells you that you have a solution that's made from sodium hypochlorite being added to water. Okay? Now, if you start with 0.60 moles of sodium hypochlorite, what is the pH going to be? Well, the first thing we got to figure out is what part of this salt is going to be involved, and is it going to be acidic or basic? Well, sodium, Na, came from sodium hydroxide, which is a strong base, so I can ignore sodium. Hypochlorite, the hypochlorite ion, came from HClO, which is a weak acid, which means ClO minus would be a weak base. So ClO minus is going to be a base, which means when it reacts with water, it's going to produce, well, it's going to accept a proton from water, so it's going to become HClO and hydroxide. And so now what you have in front of you, even though this seems like a totally different question, it's exactly what we are working with weak bases. I'm going to ice it, and then I know my initial concentration of the hypochlorite ion, it's going to be 0.60 moles divided by 2 liters to get the concentration, so that would be 0.30. Remember, I ignore water. My HClO concentration is 0, and my hydroxide concentration is 0. So what I'm going to do, I'm going to subtract X from the reactants, add X and add X to the products, which gives me 0.30 minus X for my reactants, and then X and X for my products. Now I know my base dissociation constant, so I'm going to write that really quickly. So my Kb equals, well, my concentration of hypochlorous acid times the concentration of hydroxide all over the concentration of my hypochlorite ion. Now I can put in everything I know. Well, I know my Kb, it's 3.33 times 10 to the negative 7th. I know that the top, the numerator, is going to be X times X because those are my products, so it's going to be X squared. And I'm going to divide that by 0.30 minus X. Well, using my law of 100, 0.30 divided by 3.33 times 10 to the negative 7th is going to be larger than 100, so I can ignore that X. So all I need to do now is take 3.33, multiply that by the 0.30, and then square root that. So I end up getting 9.99 times 10 to the negative 8th equals X squared. I'm going to square root that, and what I end up getting for my answer is 3.16 times 10 to the negative 4th. Now that's my concentration of hydroxide. I can now take the negative log of that and find my POH, which is 3.50. Okay? What I now can do, finally, is I can take 14, subtract 3.50 from that, and that gives me my pH, which is 10.50. Okay? So while the salt questions might look totally different, they're the same as the weak acid or weak base problems, except for the fact that you need to determine what is acting like an acid or a base. So in this case, it was the hypochlorite ion that was acting as a base. The last concept is one that is simply going to add a tiny bit of additional information for you to know. So what the common ion effect tells you is that whenever you have a weak electrolyte and a strong electrolyte containing a common ion, the weak electrolyte is going to ionize less than if it were alone in solution. Meaning, if, for example, I have hydrofluoric acid, if I already have fluoride ions, those are the strong electrolytes, fluoride ions in solution, when I'm trying to dissolve and dissociate the hydrofluoric acid, it's not going to dissociate as much. It's going to ionize less. So in order to see that, I want you to complete the first problem that I gave you without a strong electrolyte. It's just a typical weak acid problem, and then I'll work through this common ion effect with you for you to compare the pHs of the two solutions. So do the first problem without me, pause this video, and then I'll move on. So in this problem, what it gives you is nitrous acid, so HNO2, which is a weak acid. And so what you should have done is set this up. It's an acid dissociation reaction, so you're going to have hydrogen ions and your nitrite ions, and then you're going to ice it. Your initial concentration of the nitrous acid is 0.085, and then you should have completed this using the Ka and calculated your concentration of hydrogen ions and therefore your pH. The only difference here is now instead of having a 0 molar concentration of your nitrite ion, you're going to have a concentration. So hydrogen ion is 0, while your nitrite concentration is 0.10. Now I'm going to treat it just like I did before, minus X plus X plus X. So what I end up getting at equilibrium, 0.085 minus X, X, and 0.10 plus X. Now I can write my acid dissociation expression. My Ka equals concentration of H plus times the concentration of nitrite divided by the concentration of nitrous acid. Now I can plug those values in. My Ka is 4.5 times 10 to the negative 4th. Concentration of nitrite ions is 0.10 plus X. Remember, I can ignore the plus X, since if I were to take 0.085 and divide it by 4.5 times 10 to the negative 4th, that ends up being greater than 100. So I'm going to put 0.10 there, so X times 0.10, not X times 0.10 plus X, and then divide that by 0.085 because I don't subtract the X, which makes my life a lot easier. And now I can just solve for X. So X equals 0.0038. That's my concentration of hydrogen ions. And then take the negative log of that, and that gives me 3.42. So that's my final answer. Now compare that to what you originally got when you didn't start off with any nitrite ions. Which pH is higher? Make sure you can answer that when we get into class.